The broadcast is now starting. All attendees are in listen-only mode.
Hello and good morning and/or good afternoon. Welcome to ERA's webinar on the top tips for conducting DMR QA analysis. My name is Rick Persicchiti and I am an account representative here with ERA. And before I turn the webinar over to Tom Wadera, I have a few housekeeping details. First, all attendees are in listen mode. So if you do have questions during Tom's presentation, you may type them in the questions box. We will gather and answer as many questions as possible as time allows at the end of the webinar. Also, this webinar is being recorded and will be available for viewing on the ERA website. You will receive a link once the webinar recording is posted to the website. So a little information about ERA. ERA was established in 1977 and is headquartered in Golden, Colorado, just 10 miles west of Denver. Not everyone knows that our facility also includes more than 25,000 square feet of dedicated laboratory space. ERA is a provider of proficiency testing products and certified reference material to more than 7,000 environmental laboratories in more than 80 countries. Our products are available in a variety of matrices, including wastewater, drinking water, microbiology, radiochemistry, air and emissions, and soils. ERA can also manufacture a variety of custom requests. ERA is an accredited PT provider. We are also certified as a reference material producer and a chemical testing laboratory by A2LA. ERA is also registered to ISO 9001 by the National Quality Assurance Organization. In addition to serving environmental laboratories, we also manufacture TOC reference materials and calibration standards for pharmaceutical, medical device, and biotech manufacturers. I'd also like to give a brief explanation of two key terms we'll be using: proficiency testing and certified reference material. Proficiency testing is a blind standard designed and used for lab accreditation, whereas certified reference material is a standard of known value that comes with a certificate of analysis which shows the certified value and also includes control limits. These CRMs are used to check your quality control process. During today's presentation, Tom will give you a brief overview of a few key DMR QA facts and deadlines. He will then share his top tips for running the samples for pH, total residual chlorine, total suspended solids, demand, which is BOD and CBOD, and ammonia. As I mentioned, we will answer questions as time allows. Now it's time to turn the presentation over to Tom Wadera. Tom is ERA's Inorganics Product Line Manager, a graduate of State University of New York, Potsdam. Tom has worked as a chemist for more than 24 years and has been with ERA for more than 12. And now, Tom, please take it over.
Thanks a lot, Rick. Hello, everyone, and thanks for joining me today. As Rick had mentioned, I am Tom Wadera. I'm a product line manager here at ERA. I am responsible for ERA's DMR QA product line. I have conducted full-day training sessions on the DMR QA topic for about 8 years now. DMR QA is an extension of your normal testing with the added element of being evaluated on a known value to determine the accuracy of the testing being performed. So with that, our focus today is not going to be on telling you how to run your tests because you already know how to do that, but rather we're going to focus on providing some tips for perfecting your analyses to help you meet the acceptance limits for the DMR QA study. So before we get into talking about the testing itself, let's review the schedule for DMR QA 33 for 2013. And I'd also like to bring up a few key points to help you get through the study. The DMR QA 33 study does open this year on Monday, March the 25th, which is 2 weeks from yesterday. The study will close at midnight on Monday, July the 8th. What's important to notice here is that it does close on midnight on Monday the 8th, and that is at midnight in the time zone for the PT provider that you buy your standards from. So if you happen to run into any issues, remember that ERA here is in the Mountain Time Zone, so the study will close for ERA people on Monday, July 8th in the Mountain Time Zone. The next important date is that the PT providers will send in the graded reports to the permit holders and laboratories by July the 29th. The permittees are then required to send their report, their final report, to the DMR QA coordinator by August the 26th. Corrective action reports, if those are necessary, are due by October the 7th. A few logistics behind the DMR QA study. It is acceptable to use a water pollution or WP study for your DMR QA needs. If you happen to be running a WP study, please make sure you report your results by the close of that WP study and not the close of the DMR QA study. WPs that are acceptable for DMR QA use must close between January 1st and July 8th of 2013. That's important to remember that. A couple other things is what's real important is to make sure that you're going to run your analyses as soon as possible. Every year, bar none, certain things will happen. Please allow time for things to go wrong. I get phone calls every year from people saying, well, my supervisor just quit, my analyst just quit. So those are the types of things that can go wrong. Periodically, instruments will go down. You may drop a sample and need to get another one ordered. Because most of you are wastewater treatment facilities, things can go happen in your facility. Could have a bad rainstorm, things could flood, something could happen with a chemical spill, and all of a sudden you're forced to address that as opposed to being able to address your DMR QA standards. So again, I want to reiterate the importance of allowing time for things to go wrong. You have roughly 110 days to conduct your DMR QA analysis. One of the other things I'd like to emphasize and to stress is to run the certified reference material samples. As Rick had mentioned, certified reference materials are samples of a known value where you're going to receive a certificate of analysis for that known value. And on that certificate of analysis, not only are you going to get the value of the analyte that you're looking for, but you're going to get what we call quality control limits or performance acceptance limits from ERA. And those acceptance limits are values where if you get a number within those quality control limits, you can be pretty rest assured that your process is in control and be comfortable about running your DMR QA standards. I also highly recommend from a technical standpoint to establish a routine quality control process with the use of these CRMs. It can only enhance the testing that you're doing. So we're going to go through 5 topics today. We'll discuss pH, residual chlorine, suspended solids, BOD and CBOD, and ammonia. So our first topic is pH. Most everyone agrees that pH is the simplest of all lab tests, and that's true. However, pH has very tight limits in the DMR QA study. The limits are plus or minus 0.2 standard units or SU. Due to these tight limits, pH traditionally has the highest failure rate in the DMR QA study. So our points of topic are going to be designed to help us perfect our testing by maybe 0.02 to 0.03 SU for each of the topic. And if we look at the limits that we have, that's about plus or minus 10% of our range. So what we'll look over today and what we'll talk about today with respect to pH is making sure that we're checking and maintaining our electrode. We'll talk about calibrating your meter every day, the use of fresh buffers. We'll talk about temperature compensation and about running your samples at room temperature. So the electrode that you use does need routine maintenance to operate properly. The electrode readings should stabilize within about 30 seconds. Any longer than that is an indicator that your electrode might need some maintenance. So there's a couple of things that can happen with your electrode during the course of the time of your analytical work. Okay, film does build up on the outside of those electrodes, and that film does need to be cleaned periodically. I would recommend cleaning those at least monthly to allow proper contact with the sample. So what happens is when the film builds up on the outside of these electrodes, you're going to get poor contact, and what that's going to do is that's going to increase the amount of time before you get a stable reading. And the more time it takes for that stable reading to happen, the more inaccurate your testing is going to be. So cleaning the outside of those electrodes, cleaning the film on them, is actually quite simple. So there's two main ways to do that. So you want to either allow your electrode to sit in some really hot soapy water or in about a 1% nitric acid solution for at least an hour. Once you do that, you're going to want to rinse that electrode thoroughly with deionized water. That should enable you and ensure that the outside of the electrode, all that film, will be removed from your electrode. So for those of you who are using the non-gel electrodes, and those are the electrodes where you have filling solution inside of them, the inside of that electrode should also be maintained, and I would recommend on a monthly basis. What happens over time when you're using the electrode is that you're going to pull that little rubber stopper out of the hole on the side, and what's going to happen is that filling solution in there, the water in it is going to start evaporating over time. So what you're going to notice is you're going to take your filling solution, you'll fill that up to the line, up to that little hole on the side of the electrode, and then it's going to evaporate. And then you're going to fill more solution in there, and it's going to evaporate. And then you're going to fill more solution in there. So what happens over time is that you're going to get saturation of the solution that's in there. The saturation really hurts the salt bridge that's in there, and it doesn't really allow for proper contact of the sample with the electrode. So periodically also you might see some crystals sitting down in the bottom of your electrode. And what those crystals are is that supersaturation of the silver chloride solution, and that's inside the electrode. And that's a pretty good sign that it's time to clean that electrode. So what I'd recommend is at least monthly, if not more often, is to empty that filling solution out of the electrode. And I'd recommend doing that in a fashion similar to shaking a thermometer that you hold in your hand. So you want to slowly shake like you're shaking a thermometer and allow that solution to come out of the hole. Then what I'd recommend is taking a deionized water bottle and filling up that electrode, the inside of that electrode, with deionized water. Again, shake it out, similar to the way you shake a hospital thermometer. Rinse that through a second time. And what that does is kind of ensures for you that the electrode is cleaned out of this filling solution that's in there. Once you do that, you also want to rinse out the deionized water that you've now put in there. So I would recommend taking your bottle of filling solution, fill that up once with filling solution, and shake that out. That will hopefully remove a lot of the deionized water that's in there. And then take your bottle again and fill it up again with fresh filling solution. That will help to ensure that you have a clean and properly operating electrode. There are certain things you can do to check the operation of the electrode. And here's one big tip that you can do to help monitor the operation of your electrode. So what you can do is most of your meters can read not only in pH, but also can read in millivolts. So here's what I would recommend doing. Take your meter, put it into millivolt reading. Place your electrode into a pH 4 buffer solution. Take the millivolt reading of that pH 4 buffer solution. Then take your electrode and put it in a pH 7 buffer solution and take a reading. If your electrode is operating properly, the difference in those two readings should be about 171 millivolts, plus or minus about 9 millivolts. For those of you that look at slopes, that would be 54 plus or minus 3 in your slope, or 57, excuse me, plus or minus 3. So if your meter, if your electrode is operating properly, that's the difference you would see in your millivolt readings. So the second thing is pH meters are fairly stable. I'm sure as you've noticed as you're running it during the course of the week, they don't drift much. However, the pH meter may drift upwards of about 0.5 standard units over the course of a week. So if we think about the limits for pH only being plus or minus 0.2 units, a drift of 0.05 units might be about 25% of our acceptance limits, and that drift could cause a failure. So I would highly recommend, if you don't do it now, that you calibrate your meter every day that you run samples. That will help you increase your accuracy. I would also recommend that you tighten your dynamic range as much as you can with respect to running your pH meter. What you need to remember is that you've got to bracket your calibration standards around the expected value of pH. So what I'd recommend doing is to tighten your dynamic range. So generally you calibrate with 3 buffers, a pH 4, a pH 7, and a pH 10. The sample that you get from ERA will give you enough, you'll get enough volume of sample to screen the pH. What I'd recommend doing is screening that value and then getting a rough idea about what the pH is, and if your pH falls between the 4 and 7, to calibrate with a 4 and 7. If it falls within 7 to 10, is to calibrate with a 7 and 10. The next thing I'd recommend doing is using fresh buffers every day. The importance of using fresh buffers is that you want to make sure that you're not changing the pH at all of your buffer solution, which can happen if your buffers aren't fresh, so that you maximize the accuracy of your testing. I would recommend to never reuse a buffer solution. The buffer solutions themselves are very inexpensive as far as testing goes, and so I would recommend never reusing that buffer. Another thing that isn't over widely known is that the pH 10 buffer will readily absorb CO2, which will change the pH. The pH 10 buffer is the most unstable of your 3 buffer solutions. In my experience, I would recommend that once you open the pH 10 buffer, to only use it for 3 months after opening. One of the ways that you can test the pH 10 buffer to see if it's still operating properly is to run that millivolt reading test again. If you use your 4 and your 7 buffer, you've established that your electrode is working properly. What I'd recommend is taking that 10 buffer and also getting a millivolt reading on that 10 buffer. If the values, if the millivolt difference between your 7 buffer and your 10 buffer is outside of that 171 plus or minus 9 millivolt reading, that's a good indicator that your pH 10 buffer is starting to drift and to get a new one. The next important thing to think about when running pH analyses is to use your automatic temperature compensation, or ATC, and that's quite critical because small changes in temperature can cause big differences in pH readings. Your meters are designed to compensate your pH value for any temperature changes. As you can see with the buffers that you use, most of the companies that provide buffers either on the label or the certificate of analysis will show the value of your pH buffer at different temperatures. So the ATC, it can compensate for any change in the temperature. So even if you're running your samples at, say, 12 degrees, when your buffers are at 20 or 25 degrees, the ATC can compensate for that temperature change. However, I would highly recommend to run your buffers and samples no more than 5 degrees apart. And here's why. Cold samples, or a sample of a temperature significantly different than what you're running your buffers at, will cause the solution inside your electrode to change temperatures. As that temperature is changing, the pH meter is trying to adjust your pH value for the change, that temperature change, and it never really stabilizes properly. So again, I would recommend that you maybe, if you know you're going to run pH tomorrow, today, place your pH buffers and your samples on the bench the day before you run that test so that they'll be at consistent temperatures. So those topics of pH, I'm hoping will help you to perfect your analysis by, like I said, 0.02 or 0.03 units for each one of those topics. And if you've ever had an issue where you failed your pH by 0.02, I'd sure like to have those, that accuracy back. So I'd like to move on now to total residual chlorine, or TRC. The biggest challenge with residual chlorine is the stability of chlorine and the quick degradation. Historically, the majority of chlorine testing that we've seen here at ERA is performed on the Hach meters, which are very good meters. So what we're going to do is focus our talk here on both the stability of chlorine and the fact that they're run on Hach meters. So some of the things we want to talk about here is the use of organic and chlorine-free deionized water. We want to talk about not using plastics and why. Talk about running your TRC samples immediately after diluting, getting those Hach meters recalibrated and why we would want to do that, and the proper zeroing of those Hach meters. So the first tip here is that we want to ensure that the water that we use to dilute up the sample from your PT provider, to make sure that that water is both organic and chlorine free. Organic contaminants may produce a false free chlorine reading. And since we're analyzing for total residual chlorine, free chlorine is a subset of that. So we want to make sure that we're not getting any false results by having organic contaminants in our water. Also, the water that comes into your lab that goes through your deionizing process has been treated with chlorine from facilities. So you want to ensure that there's no chlorine in the deionized water that you're using to dilute up your samples. Best way by doing that is to run a blank sample of your DI to ensure that there's no chlorine in there. If you don't have the capability or capacity for making your own deionized water, you can purchase deionized water from outside manufacturers, or what we've seen in the past that works real well is to use distilled water, and you can purchase that from your local market. The next thing we want to be careful about is to not use plastics. Plastics contain what we call micropores on the inside of that. If you were ever to put anything plastic up underneath a microscope, you'd see small pores on the insides of those plastics. And those micropores are excellent places for the chlorine molecule to deposit itself. So if it's sticking to the inside of your plastic somewhere, it's not getting into your sample that you're running, and it will cause low results. So do not allow the sample to come into contact with any plastics. Avoid using plastic flasks. Always use glass flasks when you're diluting up your sample. And I would highly recommend not using disposable pipette tips, such as the ones that come with Eppendorf pipettes. I would recommend highly that you use Class A glass pipettes for your dilution, or what also works really well are gas-tight syringes. Again, we want to remember that chlorine is very unstable. It is light sensitive, and it degrades quickly when exposed to air. So this is the reason why when you're doing your DMRs, that chlorine is considered a 15-minute test. So that's why you have to run that quickly. Chlorine will begin to degrade almost immediately when exposed to air and light. ERA, my laboratory, has done some research to determine that if the sample is run within about 2 hours after diluting up, then you would expect to see no appreciable degradation. After that 2-hour period, you start seeing some degradation, and again, it might be only a few percent of degradation. But if you fail your DMR by 2 or 3%, I would hate for that to be because you didn't run your sample quick enough. Next thing I want to talk about is the Hach meters. Now, Hach meters are very popular for TRC, and they're very effective in running the test. I've noticed in looking at the data from the DMR QA study that the majority of people reporting data for residual chlorine run the Hach meters with the DPD pillows. Most Hach meters that are in use today are internally calibrated. So calibrating the meter each time you run it isn't necessary. So what Hach does is when they deliver the meter to you, they calibrate it, and they basically calibrate it by putting a solution of known residual chlorine value into it and saying, okay, I'm running a 1 ppm residual chlorine, I'm getting 10,000 counts of light. So then when you put your sample in there, if you're getting 5,000 counts of light, then the internal calibration of the meter says, well, that's half of what we used to calibrate it, so 5,000 counts would then be equal to 0.5 milligrams per liter of chlorine. So that's real nice, and it's real accurate when your meters are new or have been recently serviced. However, that calibration will drift over time, causing some erroneous readings, because the calibration of the meter and the operation of the meter itself is done by absorbing light, which is essentially inside the meter there's a light bulb. And as that bulb begins to deteriorate and degrade where you would normally get, say, 10,000 counts of light. Over a period of time for that 1 ppm standard, you might only get 9,000 counts. So the readings are going to start becoming lower and lower. So I would recommend, and I know some states do actually require this, is to have those meters recalibrated by a certified technician annually. And if you want to correlate this with your DMR QA study, I think that would be a very good idea. So most Hawk methods that go along with the meters require zeroing the instrument prior to running the samples. And so I want to take a minute or so to let you know how to zero that meter correctly. So the best way to zero that meter is to dilute up your sample, take a portion of the sample that you want to run, and place that in the meter without putting the DPD in it first. Then the meter will record any kind of interferences that it sees, and you can zero out those. Then what you want to do is add the DPD, wait the allotted time, and to allow the sample to color, and then run that again. So another important thing is to make sure that you allow adequate time for that DPD to react with the chlorine in the sample. Historically, Hawk, I believe, recommends in a lot of their methods that you allow somewhere between 2 to 3 minutes for the reaction to come to completion. Here's a tip I would recommend. Unless you are in a hurry and you don't have time, I would wait that 2 or 3 minute period and put the sample into the meter and get a reading. I would then recommend to wait an additional minute and then look at the reading again. What happens is, over time, those DPD pillows tend to weather, and chemicals will tend to weather over time. And what weathering means is that the chemical isn't as strong or as potent as it was when it was fresh. So there, periodically, as those chemicals weather, it could be possibly that it might take more than that 2 or 3 minutes for your reaction to come to completion. And that will be shown by waiting an additional minute after you take your reading. And if that chemical has weathered, your readings will start to rise. Then I'd recommend waiting another minute until you get to a point where you're seeing consistent readings, and that will let you know that the reading has come to completion. So this way, that will avoid you reporting low residual chlorine results if the chemical, the DPD chemical, happens to be weathered. So the next topic we want to talk about is total suspended solids, or TSS. This is also known as non-filterable residue. So if you happen to see on your reporting sheets or on your permit non-filterable residue, we're talking about total suspended solids, or TSS. The biggest issues that we've seen with your TSS analysis revolve around controlling your environment, TSS being a sticky material, and ensuring that you can accurately measure your residue. So to address these points, we're going to talk about using enough sample and what that means. We'll talk about rinsing our apparatus thoroughly, drying your samples thoroughly, minimizing your environmental controls, and running filter blanks in order to help with the environmental controls. So TSS is run with what we call a gravimetric tests, which means you're going to be measuring a certain amount of mass on a balance. So you want to make sure that you can accurately and appropriately read the amount of residue that's left in the pan. So what's really important in doing our TSS measurements is to make sure on our balance that you've got enough residue on the balance to accurately measure that. So I would recommend, depending on how much sample you get, is to use as much sample as possible. The more mass you have on your balance, the easier it's going to be for you to measure that. So you also want to make sure, for accuracy purposes, that you use no less than a 4-place balance. 2-place or 3-place balances may not give you enough resolution to accurately measure the amount of residue on there. Also, with your 4-place balance, you want to make sure, again, that you're putting enough residue on that balance to counter what we call balance uncertainty. And what that means, if you ever run your analysis and you're looking at your balance, if you look at that 4th decimal place in your balance, a lot of times you'll see that that number in the last place of the balance will go up 1 number and down 1 number. So let's say we're measuring something and that last place on the balance is a 4. you'll see it go from 4 to 5 to 4 to 5 to 4, maybe down to 3, and a lot of times it doesn't always stabilize in there. And that's called a balance uncertainty. So what we want to try to do to avoid that balance uncertainty and uncertainty in our measurements is the more residue that we leave on the pan, the less that balance uncertainty comes into play. So that's one of our environmental controls that I had mentioned previously. So the more mass that's put on there, the less of an inaccuracy that uncertainty of the balance will present. And unfortunately, there isn't anything you can do to control that uncertainty. So what we can do is we can minimize that uncertainty by placing more residue on the balance. Another one of the environmental controls is moisture. And moisture is inevitable in a laboratory. So if there's anybody here that's in one of those hot and humid states in the summertime, you know, where you're running this test in June and it's 90 degrees out and it's 95% humidity, controlling that moisture is a very, very difficult thing to do. So again, by using more sample and increasing the amount of mass that's on your balance, the less the moisture in your test is going to play a role. And we'll talk about a little bit about that when we talk about blanks. So again, environmental controls will play a big role in the accuracy of your TSS measurements. So I can't stress enough that the more mass of residue that is on your balance, the less those environmental controls will come into play. Another issue with TSS is, as you know, when you're doing the tests, is that TSS tends to stick to everything. So what's real important to make sure to minimize any of the sticking of the TSS powder is to make sure that you rinse all your glassware thoroughly. Anything that comes into contact with TSS, you want to make sure that you rinse it with DI water. So essentially, when you're doing your test, you're going to mix up your sample real well. So you want to make sure that you mix the TSS, and I would recommend inverting any samples that you have a minimum of 3 to 5 times to make sure that you get a good suspension. Because you want to remember that TSS is heavier than the water that's in there, so eventually it will sink down to the bottom. So after you mix your sample real well, you're going to pour a certain amount of that sample into a graduated cylinder to give you your volume, and then you'll pour the sample from your graduated cylinder into your vacuum filtration apparatus. Now what's going to happen is a portion of what's in that graduated cylinder is going to stick. So you want to make sure that you rinse that graduated cylinder a minimum of 3 times with DI water and pour those rinsings through your vacuum apparatus. You're also going to have TSS that's going to stick to the vacuum filtration apparatus. So once you've poured your sample and you've rinsed out your graduated cylinder, take your DI bottle and also rinse out the vacuum filtration apparatus to make sure that none of the TSS residue is sticking to that. Another major issue, again, as I had mentioned with TSS, is moisture. So what I'd recommend you do is to run a blank filter to determine whether you are gaining or losing moisture in your test. So very rarely when you run that blank filter does your residue on the blank filter actually show 0.0000 on your balance. It might show a small negative number, maybe 0.0002 or 3, or a positive number to that effect. The running of the blank sample is kind of a way to determine whether your test is gaining or losing moisture. And you can be pretty comfortable that if you're gaining or losing moisture in that blank sample, that is also happening with the sample that you're running for your DMR QA. So it gives you an idea about how in control your environment is with regards to that test. Now, there's really nothing you can do about it. Moisture gain and moisture loss is part of the test. But in order to help you to minimize that, again, if you increase the amount of residue, the effect of the moisture gain or loss will be minimized. Another thing you want to do is to make sure that you ensure that the sample that you're running is completely dry. So if you look at your methods, the methods will tell you to dry your sample at 105 degrees, I believe it's 103 or 105 degrees, using your normal procedures. So after you cool your sample, you're going to get a dry weight. You're going to measure that on your balance. What I'd recommend doing is once your dry weight is measured, take that sample, place it back in the oven for at least 30 minutes. cool it again, and then reweigh to ensure that you've got a constant weight. That's the best way to ensure that you've driven off all the moisture from your sample. If you don't drive off all the moisture, then you're going to end up getting high results. You also want to make sure that you use a desiccator to ensure that you're not introducing any moisture when cooling that sample. The last point I want to bring up is to make sure that you cool your sample long enough. Many of you will use aluminum pans and the 47 millimeter filter paper along with that. Those pans tend to cool completely within about 15 minutes. But some of you will use these ceramic crucibles, or what we call gooch crucibles. Those crucibles take a lot longer to cool than the aluminum pans do. So although the crucibles may feel cool to your touch, if they're not completely cooled on the inside of those walls, your readings will be affected. So, and also remember that those crucibles will cool at different rates. If you've got 10 of them, they're not going to completely cool at the same rates because they have slightly different thicknesses in them. So as a general rule, I have found I would allow those crucibles to cool for at least an hour, generally within an hour that all the crucibles have fully cooled. I would also recommend that you cool your crucibles for equal amounts of time in each portion of the drying event. So when you dry them ahead of time, if you're going to let them cool for an hour before you weigh them empty, then I would recommend letting them cool for an hour after your first drying and again after your second drying. So our next topic is BOD and CBOD. And as I'm sure a lot of you are fully aware, BOD is probably the most complex test that you're going to perform for DMR QA. It has the most places for things to go wrong, and due to that fact, it also has the widest limits of all the tests in DMR QA. So we're going to focus our content here on the main areas where things to go wrong that can negatively impact your analyses. So the first of which is to make sure that you adjust your pHs to the proper level. You also want to make sure that you set up your method properly. You want to use adequate sample sizes. It's quite important to make sure that you run a GGA standard and only use aliquots meeting your method criteria when you're calculating your BOD numbers. So the first thing is it's critical to make sure that the test that you're running on the samples your samples have a pH between 6.5 and 7.5. The reasoning for that is that you're going to be adding microorganisms to your samples, which is going to cause oxygen depletion. If your sample is too acidic or too basic, it's going to distress those microorganisms, and they're not going to work at the proper rate, and it will cause falsely low oxygen depletion, which is going to result in low BOD or CBOD numbers. ERA has done a lot of research on how to properly adjust those pH samples, the samples for pH. A lot of you sometimes have noticed in your history that you'll add a little bit of sodium hydroxide, the sample pH will rise to about 3, 4, maybe 4.5, and all of a sudden you add some sodium hydroxide and it shoots way up to 10. And then you add some acid back to and it shoots back down to 4, and you play the shooting game up and down. Well, we've done some research and we've noticed that about a 0.2 normal sodium hydroxide solution is very effective for pH adjusting. With a 0.2 normal solution for the ERA demand sample, it takes somewhere between about 3 to 5 milliliters to adjust that pH into the proper range. I do want to let you know that it is perfectly acceptable for your pH to go above that range and to go back down that range, and make sure that you find, the balance of acid or sodium hydroxide to add to get it into that range. What you want to make sure you do is that before you actually aliquot and add your microorganisms or your seed, that the pH is between 6.5 and 7.5. So our method conditions are very critical for proper oxygen depletion. So if you look at your method, and most of you will follow method 5210B in standard methods, that the initial DO or dissolved oxygen reading should be between 7 and 9 milligrams per liter. So that's a good starting spot to make sure that you can run the test properly. If your water is supersaturated with dissolved oxygen, which means that your initial DO reading is greater than 9, then you'll want to swirl your sample to release some of the air bubbles to get it within there. Your incubation period is 5 days, and you want to make sure that you're incubating your sample for the exact amount of time in the method, and you want to make sure that your temperature is 20 degrees plus or minus 1 degree C. And the reasoning for that is if your temperature is too high, it speeds up the microorganisms and you'll get too much oxygen depletion. If your temperature is too low, it slows down the microorganisms and you'll get too little oxygen depletion. For the method, your dissolved oxygen or DO difference should be at least 2 milligrams per liter, and you should have at least 1 milligram per liter of residual DO. When you're doing the incubation, make sure that you provide an air barrier on those BOD bottles to not allow any air to enter the sample during incubation. If you allow air to enter during the incubation period, you're going to be adding oxygen to the sample and you will get falsely low results. The method also stresses to run what's called a seed control. And that seed control sample, when calculated, should be somewhere between about 0.6 and 1 milligram per liter. Please remember that your seed will inherently contain BOD. So there is going to be some low-level BOD in the seed itself. With the seed, I would highly recommend that you use the same amount of seed in all your samples. Because your seed is going to contribute a certain amount of BOD to the sample, you have to subtract that out before you report your results. So you're going to need to blank correct for that seed value. If you use different amounts of seed in each of your samples and a different amount that you used for your seed control, then it's going to affect how much BOD is being contributed by your seed. So what's real important with your seed is to make sure that you're using enough seed to facilitate the oxygen depletion of your sample. Now there's two main seeds that you can use. One is a poly seed, which is a commercially available seed, and one is your raw influent. And a lot of the plants have really good raw influent, and that seed tends to be a stronger seed than the poly seed. So you're going to need to adjust the amount of seed that you use based on the type of seed that you're using. Make sure you spike each bottle individually with seed. Don't spike the diluted sample with seed. The reasoning behind that is you're going to use different aliquots of the sample in your BOD bottles. So if you were to spike the sample itself and not each individual bottle, you're going to be adding different amounts of seed and it's going to affect your values. You also want to make sure that you run what's called a glucose glutamic acid, or most of you know it as a GGA standard, to check the method. This will determine if your method is in control, and that's required by the method, and it's the one true way of making sure that your process is in control. So what's going to happen when you run your BOD is you're going to run a series of different dilutions, and you're going to determine in those dilutions which ones you're going to report for your BOD or your CBOD value. So when determining which aliquots to use in the test, you want to make sure that you have enough sample to meet the 2 milligram per liter depletion and that you do not use too much sample so that you're left with a less than 1 milligram per liter residual. So make sure you use enough dilutions so that you're meeting both those criteria, that you have one where you've got enough sample for the 2 milligram per liter depletion and that you've got enough aliquots so that you don't have all of your samples where you're leaving less than 1 milligram per liter residual. And when you're calculating out your final numbers, only use those aliquots that meet the method criteria when you finally determine which ones to report. So our final topic that we're going to talk about today is ammonia by ion selective electrode, or ISE. The main issues that I've seen with ammonia is with the operation of the electrode itself and your testing conditions. So we're going to talk about changing the membrane often, how to slope your electrode, the appropriate calibration of your meter, making sure that you're adjusting the pH appropriately, and the importance of maintaining a constant temperature in running your ammonia. So your ammonia electrode has a membrane, uses a membrane that measures partial pressures on both sides of that membrane. So on the bottom of your electrode, you'll have a membrane in there. The filling solution that you have puts a pressure on that membrane, and since that filling solution has a constant amount of ammonia in it, it's putting a constant pressure on the inside part of that membrane. The samples that the samples themselves that you run also put a pressure on that membrane, and it puts a pressure on the opposite side of the membrane than your filling solution. And what the electrode is measuring is it's measuring the differences in the pressures from the inside to the outside of that membrane, and that's how it lets you know what the ammonia value is in your sample. Well, over time, that membrane will clog. You know, the filling solution, the sodium hydroxide and the methylene blue in those solutions will tend to clog the pores of that membrane. So I would recommend that you change that membrane at least weekly, so that you can minimize the amount of clogging, and thus reducing, as it clogs, it reduces the ability to measure that partial pressure. So you want to reduce that issue by changing that at least weekly. You also want to make sure that the electrode is functioning properly, and you can do that by performing what's called a slope on the electrode. So this is done by taking 2 different aliquots of ammonia, and you want to take 2 different aliquots with a 10-fold change in concentration, such as using a 10 and 100 part per million ammonia solution. And so what you'll do is you'll spike the 10 ppm solution, you'll get a reading, a millivolt reading. Then you want to spike again with a 100 ppm or a 10-fold change in that dilution, and you're going to get another reading. For your electrode to be operating properly, the difference in those 2 millivolt readings should be somewhere between 54 and 60 millivolts. That lets you know that the electrode is working properly. If not, that's an indicator that probably more likely than not there's something wrong with your membrane and you need to change that membrane. You also want to make sure that the meter is calibrated appropriately and calibrated each time an analysis is done. You want to observe the calibration range for your analysis. And what I mean by calibrating appropriately is the smaller the dynamic range, or the smaller the range of ammonia that you calibrated in, the more accurate your curve is going to be. So for example, for your DMR QA, the values of the ammonia are going to be somewhere between 0.65 and 19 milligrams per liter. So you want to adjust your calibration to make sure, one, that you're bracketing those values, but that you're putting a smallest dynamic range possible to enable you to get the most accurate range. So for example, if you're going to be somewhere between 0.65 and 19, calibrating your meter from 1 to 100 might be too wide of a dynamic range and can cause some inaccuracies in your analysis. So it might be good enough for your DMRs, but when you're trying to hit a value within a specified range, the smaller the dynamic range, the better. So want to talk a little bit about what you're actually measuring. So ammonia testing is actually measuring not ammonia itself, but the ammonium ion. And the ammonium ion is volatile at a pH greater than 11. So to avoid a low reading measure, you want to make sure that your pH is greater than 11. A lot of manufacturers, Orion being one, supplies what they call an ionic strength adjuster, or an ISA solution. Most of you will see that as a blue solution. And that blue solution contains what's called methylene blue, which is designed to stay blue at a pH greater than 11. But if your pH is less than 11, the solution will turn clear. So if you're using that blue solution, as you spike it in, make sure that it's staying blue, because that's a representation of your pH greater than 11. Some of you will just use sodium hydroxide solution. That's also okay. But what's important in adding the sodium hydroxide is make sure that you're checking the pH of the sample to assure that it's greater than 11. Since you need to mix your samples when you're testing the ammonia, your samples are going to need to be stirred. Stirring the samples will cause some friction in the stirring plate. That friction causes heat, and heat can possibly change the temperature of the sample that you're running. And a change in temperature can cause, again, a change in your values. So what I'd recommend is to prevent any heat transfer from going to the stir plate to the sample itself, is to place some kind of a material on the hot plate which will prevent that heat transfer. Some cork board works real well. Packing material works real well. Something that'll trap that heat transfer. A 1 degree change in temperature can change your values by as much as 5%. Another important thing is to remember how to report your results. You're going to be reporting your results results ammonia as nitrogen and not ammonia as ammonia. So you need to make sure if you're calibrating as ammonia that you convert your results over to nitrogen and not ammonia. There's about an 18% difference or so in your values if you're not doing the conversion properly. The final point is technology has advanced itself that a lot of the manufacturers make what's called a high-performance electrode. And these high-performance electrodes allow you to get much lower readings of ammonia. However, they're significantly more sensitive and they do drift fairly easily. One of the important things to remember is that with these high-performance electrodes, the instrument manufacturers will tell you not to rinse the electrode itself with DI water. The pressure of the DI water will cause that electrode to drift, and once it drifts, you're going to have to perform your calibration all over again. So what they recommend is to not use your DI bottle to rinse it, but to dunk that electrode into a container of DI water and then dab dry with a chem wipe. Okay? So we've gone through all our topics, and it looks like that we have received several questions in that have come in during the course of our talk today. So I'd like to take a few minutes to address as many of those questions as possible with the time that we do have remaining. And I apologize ahead of time if I do not get to all the questions that were sent in. But if I don't get to them before the end of our presentation today, I will address those questions after our webinar. And I will post the questions and answers to those questions on the ERA website. So it looks like we've had a couple of people talk about adjusting the pH for BOD and how to do that. And it looks like I've got Adam and Joe from Illinois that have asked about adjusting the pH for the BOD. And as we had mentioned, it's critical to make sure that that BOD is adjusted properly. And I want to make sure, again, that it is okay to overshoot that pH range, that 7.5 range. And even if you're playing the game of going above and going below, and going above and going below, it's perfectly acceptable for that to happen. The important thing is that you make sure that before you do the testing itself, before you lay out your aliquots, that you make sure that the pH is between the 6.5 and the 7.5 range. It looks like we've also got a number of questions talking about the paperwork. Since we focused today on the analytical part of the process, I'm going to take a couple of minutes to really talk about the paperwork. So we've had about 5 or 6 different areas of the paperwork it looks like people have some questions about. So the way the paperwork works for the DMR QA study is that when you order your samples from your PT provider, regardless of who you get them from, you're going to get data reporting sheets along with them. So when you run your analysis, you can fill out the information on the data reporting sheets, or you can go to the PT provider's website and report your results on the website. So the first important part of the paperwork has to do with reporting your results first. So each laboratory who receives sample, whether it's you as an in-house laboratory or a commercial lab, which that you have outside labs work for you, what we call your contract labs, each laboratory is going to get their own samples and they will report their own results to the PT providers. The PT providers are then going to send back to you and to your contract labs the graded reports. And that's the report that says whether you passed or failed each particular analyte. So once you get that report back, what you're going to do as a permit holder is you're going to compile some information together. And the report that gets sent to the DMR QA coordinator is going to contain the 2 EPA cover sheets. The first of the cover sheets from the EPA is going to have your permit information on that, where you fill out your permit number, you fill out your physical address, and you fill out the information of who is the contact for your laboratory. So that's the first sheet you fill out. So regardless of how many laboratories you have doing testing for you, you're going to only fill out one of that first cover sheet, and then your second page of the cover sheet is going to list all of the laboratories that did testing. So you will list there your in-house laboratory, You will list any contract labs who did chemistry testing for you. You will also list any laboratories who did microbiology testing for you, as well as any labs that did wet or whole effluent toxicity testing. So what you're going to send to your DMR QA coordinator is one report, and that one report is going to contain one copy each of the 2 EPA cover sheets. There's also in your 308A letter that you've received from the EPA, there are going to be checklists. And you're going to have one checklist for chemistry and microbiology and one checklist for your wet testing. So with that, you're going to make one copy of the checklist for each laboratory that did testing for you. So if you have your in-house lab and you have a contract chemistry lab, say for your metals, and a contract chemistry lab for your microbiology, you're going to make 3 copies of the checklist for chemistry and microbiology. And on those checklists, you're going to check off the analytes that were reported by each of those contract labs and whether they passed or failed. So for your in-house lab, you're going to have a copy of your checklist and the tests that you did in your in-house lab. With that checklist, you're going to submit one copy of the graded report you got back from your PT provider. Then you're going to make a second copy for any of your contract labs and include the graded report from your contract lab. So it's important to make sure once those graded reports come back that you get a copy of that graded report from your contract labs. Then if you happen to have any whole effluent toxicity, you would make a copy of the checklist for the whole effluent toxicity tests along with a copy of the graded report for the wet testing. So that is your entire report that needs to be sent to your DMR QA coordinator. And it's only one copy. That's all you need to send. So one of the questions I got is, what happens if my lab, my in-house lab, and my contract lab use different providers? That's not important this year because your contract lab, say you use ERA for your samples, and you're going to get a report back from your contract, from ERA, a graded report back. Then you have a contract lab who happens to use a different provider. They're going to get a graded report back from that provider, and they are going to forward that report over to you. So regardless of how many different PT providers you're dealing with, you're going to send one copy of the checklist from that lab along with their results, their graded results, to your DMR QA coordinator. So one report. And also, you're going to need to make sure that you keep a copy of your final report in your facility. So you want to keep one report for yourself and one report from, send one report to your DMR QA coordinator. The other thing that you're going to have to deal with is corrective action. So I've got a question about corrective actions, who needs to do them, and what needs to be done with that. I got that question from Mark in Louisiana. So Mark, what you're going to need to do, and anybody else that has questions with regards to this, is any analyte that comes back with a graded report of not acceptable, you're going to have to do a corrective action for that analyte. Now, the corrective action that needs to be done is going to vary by state. Each state will require something a little different. So you'll need to check with your DMR QA coordinator whether you need to analyze an additional sample or just provide some kind of a corrective action report. But your corrective action report is going to consist of saying what you did to correct the problem that resulted in your not acceptable value. And then you're also going to need to submit some kind of proof, and again, each state is going to be different with what they require, some kind of proof to show that you corrected the problem. So you're going to have your report plus your evidence of your correction of the problem, and then that will need to be submitted to your DMR QA coordinator. So the paperwork is going to be fairly easy this year with respect to that. So it looks like we've come to the end of our time together. I want to thank you very much for spending the last hour with me. I hope you're able to pick up some pointers that will help you during your testing. So I did want to take a minute, again, to reiterate some of the important points of DMR QA. The study does open on March 25th, closes at midnight on July 8th. ERA is open until 6 p.m. Mountain Time so that you can place your order with us at any time between 6 a.m. and 6 p.m. Mountain Time. Also, please make sure you remember that ERA is available to ship you samples up until the day before the DMR QA study closes. So if you've already received your PT samples and something happens to go wrong and you do need additional samples, ERA can overnight ship samples to you so we can sell samples to you up until July the 7th. Again, you're going to receive your graded reports by July 29th. Your final graded report to your DMR QA coordinator is due by August 26th. Your corrective action reports, if necessary, are due to your DMR QA coordinator by October 7th. Again, please make sure that you conduct your analyses as early as you can and allow time for things to go wrong so that you're not scrambling at the end of the study. And myself and ERA, we highly recommend the use of the certified reference materials as a normal routine QA/QC program. This will help enhance your testing process when it matters the most. If you're interested, please call the ERA customer service so that you can sign up for a CRM subscription service. So thank you once again. And in conclusion, if you have any questions or you need any information, the ERA contact information is up on the screen, and you can contact us at any time. And this concludes the webinar on our DMR QA analysis.